Okay, so we are now looking at product spaces. So we have XS and YT measurable spaces. So measurable rectangle is of the form A cross B, A in S, B in T. And then elementary set equals finite disjoint union of measurable rectangles. And then, so this is E, elementary sets. Then S of E, the sigma algebra generated by E, sigma algebra generated by E, and that is denoted by S cross T. So this is the sigma algebra we put on X cross S. Okay. So now we have a definition. XS YT measurable spaces. F from X cross Y to R given function. X in X, Y in Y, then the X section of F denoted F sub X is defined by Fx of Y if F equals F of X Y, Y in Y. Similarly, the Y section of F define Fy. Okay, so since I have used, let me put Z. Fy of Z equals F of Zy for every Z in X. Okay, so this is these are the two sections of the function. Just as we defined X and Y section of sets, we have sections of functions. Okay, now we have three measurable spaces. So we have XS, we have YT, then we have X cross Y, S cross T. So when I say measurable, I will have to say in where it is measurable. So I will say S measurable, T measurable, or S cross T measurable, depending on the context. One can understand then where these functions are and how they are measurable. Okay, so now we have a proposition. Just as we had a proposition for the test of measurability of sets, this proposition gives you a test of measurability of a function. Okay, so XS YT measurable spaces. F from X cross Y to R and S cross T measurable function. Then for every X in X, for every Y in Y, F sub X and is T measurable and F super Y is S measurable. So proof. So again, why is this a test of measurability? If either of these sections are not, if even for 1x or 1y the corresponding section is not measurable, then the original function cannot be measurable. So this is how we use it to test for measurability. So let C belong to R. Okay, then you take Q equals set of all xy in X cross Y such that F of xy is bigger than C. So this is S cross T measurable. Then For every x in x, qx is t measurable. But what is qx? So this is set of all y in y, so set xy belongs to q. Which is equal to set of all y in y, such that f of xy is bigger than c, that is equal to set of all y in y, such that f sub x of y is bigger than c. Okay, so this is t measurable, and therefore this implies that fx is t measurable. So for every c in R, this set is measurable, and therefore that by the definition fx. So similarly, fy is s measurable. Okay, so now example, xs yt measurable spaces, f x to r s measurable, g from y to r t measurable. Now let capital F of xy equal to f of x. Okay, we are defining it, it's independent of y. Okay, so set of all xy belonging to x cross y such that f of xy is bigger than c is set of all x in x such that f of x is bigger than c cross y, and this is a measurable rectangle, and therefore capital F is s cross t measurable. Similarly, g of xy equals gy is s cross t measurable. Now product of measurable functions is measurable, so xy going to fx gy variable separable case is s cross t measurable. So you take a measurable function in one variable, measurable function in another variable, multiply them, you will still get a measurable function in the next. Now R equipped with Borel or Lebesgue sigma algebra. XS measurable space. Now f on R to x, R cross x to R, a given function such that for every x in x, the function t going to f of xt, f of tx is continuous. For every t in R, the function x going to f of tx is measurable, s measurable. We have seen an example of thing earlier. So such a function is called a Karateodori function. A function in two variables, continuous in the real variable and measurable in the other variable, is called a Karateodori function. Okay. So claim f is continuous on the product, f is measurable on the product space. Whether you put Borel cross S or Lebesgue cross S, it doesn't matter. Whatever it is measurable. Okay, so we want to prove this. So R equals union k belonging to the integers of k minus 1 by 2 power n, k by 2 power n. Okay, you can take it either way like. So let us take it open here and take it closed here. So I am dividing the real line into subintervals, each of length 1 by 2 power n, very small when n is large, and then R is the union of all these semi-open intervals. Now you define Fn of Tx equals f of k by 2 power n x if t belongs to k minus 1 by 2 power n, k by 2 power n. T will belong to exactly one of these intervals, and therefore you have that it is given by this. So we can write Fn of Tx is sigma k in Z f of k by 2 power n x into chi k minus 1 by 2 power n, k by 2 power n t. So this is measurable, S measurable, and this is of course T measurable. Whether it's Lebesgue or Borel, it doesn't matter. Now by previous example, each term is measurable, and that implies that Fn is measurable in the product space. Because you take any finite combination that is measurable, and then you take n partial sums are all measurable, and then you let n tend to infinity, the limit is measurable. Okay, so now you take T naught x naught belonging to R cross x, epsilon greater than 0 given, then there exists a delta positive such that mod T minus delta less than T minus T naught less than delta implies mod f of x naught T naught minus f of x naught, T naught x naught minus f of T x naught is less than epsilon, because the function is continuity, comes from the continuity. Okay, now n large enough such that 1 by 2 power n is less than delta. Then what is f of T naught x naught minus f of Fn of T naught x naught? Now you have to see, so T naught will belong to some k minus 1 by 2 power n, k by 2 power n, and then Fn of T naught x naught is f of k by 2 power n x naught. Okay, so this is equal to mod f of t naught x naught minus f of k by 2 power n x naught, but t naught minus k by 2 power n is less than or equal to 1 by 2 power n, and that is less than delta. Okay, and therefore you have that this is less than epsilon. So this implies that Fn converges to F pointwise, implies F is measurable in the product space. So this is an important example. So if you have continuity in one variable and the real line has Borel or Lebesgue sigma algebra, measurability in the other variable, then the function is measurable in the products. Okay, so we will continue. So next time we will try to construct a measure on the product sigma algebra which comes from the two measures mu and lambda on the original spaces.